I'm gonna pass the ball off to Pontus and let him take us into the home stretch here, talking about the science traceability matrix and sort of what we've all kind of collected and discovered and added into the discussion this week.
Thank you. Andrea, can you make me co-host? For some reason, it's disabled.
I'm afraid Michael will need to do that.
Michael, what do I owe you for making me co-host?
Good food in New York City next year when we hold the workshop again.
The Halal Brothers.
That's
remember?
right. Halal guys. Co-host. There you go.
Okay. Let me try this again. Here we go. Yeah, this works. Okay. Let's see if we can wrap this up. So as Michael said, this is going to be more of a science wrap up. There's been tremendous amount of discussion, tremendous amount of comments. I'm not going to make it too lengthy, I think, because I know everybody's tired. Here we go. All right. So
wait, everybody's tired, but they're going to get mad at me. I only got the second of those two screenshots. Can we do this again? I'm sorry. It'll only take a second. Pontus, you have to stop sharing. Okay.
Yes, I know.
Forgive me. I thought I had it and I saw it, but then it did not stick. All right.
All right. Press harder this time.
All righty. Ready? 3, 2, 1. All righty. And one more time. 3, 2, 1. There we go. Okay. My apologies, everybody. I should never be the cameraman. We already know this.
Yes,
please proceed.
Okay. All right. Let me reshare. All right. So let's get this show on the road here. Let me see how I move this out of my way. There we go. Okay. So a lot of comments. I think we have already over 100 comments. I'm not going to talk about those here really, just some highlights. But let's talk about the science traceability really quickly here. My first lessons learned here is, yes, we did indeed get about, I think, 50 comments on the science traceability matrix overall. But I think it's true to say that once you put a monster spreadsheet like this online, nobody really looks at it because it's too big. So one of our actions on our side is to make this more compressed and more viewable, but the structure I think will remain the same. So depending on who's on here, you may want to chime up. I have just grabbed a few highlighted related science discussions here. Let's start with the fields group. There was a lot of talk, of course, about the need for low field magnetometer measurements. The flux gates that were flown on Voyager was sort of barely enough there. So there might be an option for technology development and improvements in that area to optimize that science. Obviously, for that group, it's the 50-meter wire antennas that are driving everything. They are required for getting the quasi-thermal noise to get the plasma densities. There was also talk about optional sounders. A lot of good discussion in that. And also in that, if Stuart or Bill is online, you also discussed the capabilities with shorter rigid antennas, but that's something also that we need to really put down on paper as well. For the particle group, the particle group ran over by, I can't remember, 1.5 hours maybe. Some of the takeaways there, one thing we need to discuss more is plasma charge states and how that also affects the allocations and the instruments that we have in mind. Another big one here that I think Casey brought up, if you look at the STM, we have basically helio, planetary, astro. Are we stovepiping that traceability matrix too much? In my first gut reaction was, no, we don't. And a great example of that is, of course, Casey, it's the dust. because we show the three facets or three sides of the dust question in the helio portion. That's the interaction with the heliosphere. It's the dust disk, and then in the astrophysics portion, it's the composition of dust that lends us information about the galaxy as a whole and their formation. So I think that works. And I'm going to sort of leave the floor open for comments from Casey and maybe some others on this stovepiping. Feel free to speak.
Well, if you'd like a comment from me, the stovepipe, this current stovepiping, I understand, because that's, if you will, that's a bit of how our sausage is made and how we're going to relate our science plans, our engineering plans to headquarters, 3 different divisions. If you attended either of my talks, you'll see that it actually made things very difficult because the science is so spread out across the STM and all these different colors and different divisions you have put in. That, as you just pointed out, we had to talk about extragalactic and galactic dust at one point, and then talk about solar system dust, and then talk about dust in the heliosheath and the heliopause. These were all different topics I brought together, so it was a very polyglot group that I had to address. And it does make the STM challenging, but I actually like the way that you responded. It was Michael Zemkov who brought up the question of whether it was too stovepiped in the dust science section. And your response was actually, I think, relatively telling. Not only do we, yes, maybe these are somewhat artificial boundaries because we're talking to headquarters and dust science covers all these different disciplines, but you basically said it showed how rich the dust science was and how important it is to this mission. And the fact that it isn't just in one science discipline, all the science disciplines are interested in it. And I think that's a fair response.
Yep. So basically my takeaway is that once we show those sort of 3 goals that are according to the divisions almost, we actually emphasize the cross-divisionality. So if there are no major objections, I would like to keep that structure.
No, they're not. In fact, I've gone so far as to adopt it. And you've heard us, for example, talk about this infrared spectral mapper. It's made me realize that maybe you've been talking about it mainly in the context of doing the solar system's debris disk. Well, it also is very important to actually seeing the role of dust in the heliosheath and the heliopause, as well as looking out in the galaxy and getting the extra background light. It's going to cover all those different divisions we just talked about and different time portions of our mission. So I think it's actually a good way to go.
Yep.
And I'd like to double down on that a little bit. The composition of dust near dwarf planets and other trans-Neptunian objects is a huge boon to spectroscopy, so that you can literally ground truth by tasting the composition of the dust, what your infrared spectrometers are measuring on the surfaces of trans-Neptunian objects and dwarf planets.
Yeah, and that just came up in this mission, this workshop, that we need to add that to the STM.
Okay, very good. I need to go on here because I have a few slides that I want to go through. There was a whole lot of talk about priorities and increased priorities, of course, on the plasma wave antennas that I think they're already working on, but also on ENA low, NMS, and the Lyman alpha. If you are online, if you want to say a few comments about that, you can or cannot. I know this is being worked on. Is Andre online, perhaps?
Yes, I'm here.
Good.
Yeah, of course, our topical group on neutrals felt that, how to say, the prospects of the interstellar probe for in situ measuring the interstellar neutral material as we go out, and then in particular when we're outside the heliosphere, that this is really one of the main selling points of the whole mission, and that this should be stressed a bit more than it was in the previous version of the science traceability matrix. And of course, measuring neutrals can be done and probably must be done with different instruments. Actually, we have here listed several. So we have the ENA low imager, which is also very useful to measure the spatial distributions of the primary and secondaries of the interstellar neutrals. And of course, sort of what most people first have in their mind when they hear about neutrals, a neutral mass spectrometer, which is vital to actually get the chemical and isotopical composition of the whole stuff. And of course, also related to that is the Lyman alpha spectrograph, which is a different way of measuring neutrals, but it's also measuring neutrals. You get a line of sight of neutral hydrogen. So yeah.
Anything to add, Elena?
In addition to that, Lyman alpha gives you the global picture instead of just in situ.
Yeah, that they complement each other. So you have again this in situ and remote sensing.
Mm-hmm.
Yeah, we identified a number of questions that we think important questions that we think are missing in the STM. So it was very productive.
Okay, very good. Actually, one concrete outcome I think that would be very helpful is that if we can then formulate on a piece of paper that elaborated trade or science case, if you will, between, well, targeted to neutrals. And then we can use that trade, and we want to stick that in the next report.
Yeah, I will discuss with Andre to get together for 2 topical groups and discuss this important trade between ENA low, neutral mass, and Lyman alpha. We haven't done it yet.
So yeah, maybe it's at least our 2 groups, but since we're talking about ENA low, maybe also the ENA group by Bob should be involved.
Yes,
so.
Absolutely. Okay, let me just go on. So,
but may I say something?
Yes, please.
Concerns phases. Seems to me that quite natural is that we have in fact inner heliosheaths and outer heliosheaths. I understand that everybody agrees as concerns the inner heliosheaths, but some discussion was about the outer heliosheaths. If we have bow shock, then definitely this bow shock is because the interstellar medium is supersonic and have this heliopause or the whole heliosphere, which is kind of obstacle. So outer heliosheath also is connected with the heliosphere. If even we don't have bow shock, still we have perturbed interstellar medium because of this fact that this obstacle, the interstellar flow must, how to say, obey, right? So seems to me that we still should keep these 2 regions, inner heliosheath and outer heliosheath, which means that between the heliopause and up to the whole perturbed interstellar meter, this is the interstellar medium, it is the outer heliosheath.
Yes, I understand these comments, and we've gone back and forth with them. Okay, so let's discuss phases now for a little bit. So I think the whole problem is we don't know, right? We only know what is up through the heliopause and where the Voyagers are today, right? And I also think once this mission gets refined, of course, the phases may get refined, but I do think that for the study going forward, these 3 phases that I have on the screen, they make sense in the traceability matrix because they match up better with the science measurement requirements, and that's my target here. And so if you put the 3rd phase beginning at the heliopause or so, that really takes you up to the unknown, so to speak. So also, if you look at the science traceability matrix for that 3rd objective that we have, which is in the interstellar medium, that's actually where we put the questions about the nature of the bow shock, the hydrogen wall, and the rest out there. So it's more of lumping it logistically in the STM. Do we have any other major comments about these phases?
Yeah, this is John. Can you hear me?
Yes.
What about, since we are using SLS here, what about, sort of cross-cutting to human exploration, specifically the GCR measurements beyond the heliopause, as a benchmark, for models for a very long time, the lifetime of interstellar probe.
GCR measure, are you talking about the phase definitions here, or are you talking about just in general?
I guess I'm talking about adding, making sure that the connection to manned space is made at least through the GCR part of the measurements.
Yep, that's a connection that we could make in the traceability matrix and in other documents, of course.
Yes.
But,
particularly Interstellar as being, the best upstream measurement of the
right.
cosmic rays.
Yep. Yeah. But if no other major objectives, I think we should just move on with these 3 definitions and distances, because it's about organizing not only the mission architecture study, but also the STM.
And
yeah, I think
Pontus,
that looks good, Pontus.
yeah, and just this aligns with the definitions that Tom had recommended we follow earlier in the week. Yes.
Yes, it also follows what Bill Kurth and I think also Jonathan Slayman have said as well.
Not just Tom. Yes, some of that's great. Thank you.
And I like.
Looks great.
Okay.
And before you move on, real quick,
Okay.
John Cooper.
And
Thank you very
One
much for
quick
your-
thing, this does kind of imply a noseward trajectory.
Can I add just a brief comment here, just to about these phases? The problem, I think, is that Interstellar, I think, is very good because, first of all, it's very unlikely that the spacecraft will actually enter into the pristine interstellar medium. This is too far away. And from this perspective, we'll be analyzing interstellar medium perturbed, of course, somehow by the presence of the heliopause, but in different way for different energies, different particles, for neutrals and so on, pickup ions. So I think it just makes sense to have separately heliosphere and the heliosheath, but interstellar, we don't need to add outer heliosheath because probably this is all we have.
Yeah. It is what we know today. So
yeah,
I completely agree with that.
I agree completely. Yeah.
Bob, you had something. I'm sorry we cut you off.
Yeah, just that the 120 AU is going to assume a Voyager-like noseward trajectory, and I just don't want to be complicated if we go farther off into the flanks and have to change to some estimate.
Yep, you're absolutely right. So baked into all of this, and also baked into to the STM, it's that example baseline direction. Of course, it's not exactly 90, it's not exactly 120, but the termination shock and the heliopause as we know it today, those are the boundaries. Okay, let me go on.
Okay.
Let's touch on mission success criteria. So as we talked about from the beginning, for now we set the mission success criteria as the threshold mission success criteria for simplicity, and to answer 2 questions under each objective. And then under each question, we must meet at least 1 priority 1 measurement. And so I've taken a quick look at the different combinations here. There's several different combinations, but there are just a few down here on the screen. And if you take a look at those combinations of measurements that could achieve mission success, they make sense. And also the strength here is that you have flexibility to combine different measurement types, of course. There was some concern that we set the floor of threshold mission too low. There's always this balance of if you set it too low, then you signal, of course, that, well, then you don't need much instruments to achieve the mission, which is not really true. And if you set it too high, on the other hand, you run into the problem of the all or nothing approach, where you don't allow for any flexibility in there. Have people had a chance to think about this more? To me, this sort of strikes the balance. We can sure refine it, but you look in the boxes here, you have a handful of instruments in each box. And they're sort of the the usual suspects, if you will. And if you also look closely, they actually go through all of the instruments in the example model payload, if I'm not mistaken. Okay. All right. So let me repeat to everyone here, and I hope also Jim is online as well, and Gabe. So there's been a lot of sort of misconceptions here that that we're only doing a spinning or only doing a 3-axis. But let me repeat again: we're running 2 scenarios here. There's no scenario that is going to sort of win over the other. This is a trade study again. So let me repeat: the baseline study scenario that's under study now is spin stabilized. The normal spin rate is about 1 RPM, which seems to satisfy most of us. And it has the 50-meter plasma wave wire antennas, 4 of them. Oops, hang on, let me go back. After this workshop, we are going to study then the augmentation, which has the rigid 10-meter wire antennas. And again, let me repeat, this is a 3-axis dual mode spacecraft. And what do I mean by that? Well, it means that it will be spinning most of the time. And it will go into 3-axis steering or tracking mode once you do the flyby of the KBO. Once you're done with the flyby, you spin up again. And if you don't have any further flybys, you'll stay spinning. And that sort of requirement comes, of course, from a lot from the heliophysics, but it's also for stabilization purposes of the spacecraft.
We have a quick question from Gabe. Does 1 RPM, is that fast enough for the wire antennas?
Yes, yes. Let me loop back on that. As I understood it from Stuart and his group, you require about 5 RPM, at least when you deploy this. But then after you've deployed it, you then slow down gradually to 1 RPM. Is Stuart online? I don't think he is. I didn't see him.
He had to leave, Pontus.
Okay. Okay, so I just want to sort of reset that thinking again, that these are the 2 scenarios that we're studying.
Yeah, so Pontus is Jim. If I could just jump in for a second, I think what we'll find for the second case that we're working, that's the hybrid mode or dual mode. It's not just going to be during the planetary flybys when we do 3-axis, but there may be short periods of time when we want to do that for other reasons as well. There's a comment in the chat from Kirby about Astro.
Yes.
That's one possibility. The other possibility is there may be times for communication purposes, for instance, that it would be useful to spin down and use 3-axis control to get higher data rates. I'd have to look at it. But point being, it's not that we would never spin down again, but there would be very limited times when we would, in between those limited times would be long periods of times when we would be in spin mode. That makes sense?
Yep, absolutely.
Jim, this is Casey. I'm going to chime in for Astro. You're exactly right. If we want to, for example, make the look back image of the Zodi cloud around the sun with the planets in it that Pontus and Ralph have been asking for, we need to have that be in 3-axis for that.
So the one that we will need to understand that comes out of this is what a ConOps for that would look like. How often would you want to do that? And so forth, because of course you're spinning propellant every time you spin up and spin down, right?
Astro has one other, okay, sorry, go ahead.
Now, I was just going to say, so we'll need to understand that as we're going into the engineering concept.
And Astro has one other question. 1 RPM may be a bit fast for our applications in cruise. Is there a way to get to 0.1 RPM or to slow down sometimes to that, but not stop?
Or the augmented scenario.
For the augmented scenario.
Yes.
Yeah, for the augmented scenario, it's there would be no sort of hard and fast requirement on what the spin rate would have to be, other than just sort of what's the capability of the spacecraft on the upper end. The problem with the Helio case with the wires is we have to maintain a minimum spin rate to make sure we've got proper tension to keep them from going wacko on us.
I understand. So can you give us a better feeling for what that lower limit has to be?
not right now. I can't. That's something we got to work, I think, with the folks who know about the wires.
Okay, so I'm just doing the best job
I
of
would
representing
say-
my constituency. I just want to point out is lower is better. Lower, much lower, factor of 10 lower than 1 would be good if possible.
Yeah, I agree with that. My only concern is that I don't think that's going to be sufficient for keeping the antennas deployed.
Understood.
So Jim, this is Mike Zemkoff. I asked Ralph yesterday, and I'll ask you directly. We should probably talk at some point if that's possible.
Sure, happy to do it.
Yeah, so I have the information from Stuart about the minimum spin rate.
Thank you.
My memory says it was at 1 RPM, but I'm sure as we can dig that up again. And also just to what Casey said here, that sort of look back image that we've talked about, not yet really explored. I talked to Gabe about it a little bit, and Jim, is to be beyond the dust cloud and look back and scan with a potential IR detector to get that first image of the dust disk. And if that's possible, I think that would be very, very valuable for just selling a mission like this.
Yeah. So as I said before, in the dual mode or hybrid mode, something like that is certainly doable. It's a cost to propellant, so we just need to understand how often you'd want to do it, and just make sure we factor that into the delta V in the propellant budget.
Great. I think that would satisfy a lot of our needs. If we can get the spin rate down during cruise, that's the rest of it. Or if there are times like maybe once a few weeks every year, if we can slow down the spin rate, you don't have to stop, but slow it down so that Astro can do its science and then just speed up again. That's a good compromise we can probably live with.
Yep, this is a great dedicated discussion to have offline. Okay. So let me remind you of other scenarios that have been discussed. The idea of deploying 50-meter wire antennas after the KBO flyby, it came up actually last year, and we already last year said this is too high of a risk for a mission. We will not study it, but it will be documented in the report. Anything you want to add to that, Jim?
No, I think that's fine. We, as part of the documentation, what we got to think about is not just sort of the aging effects and things like that, but also the fact that you are now much further away from the Earth when you're trying to deploy these things. And so there are comm issues associated with that. Sort of worrying about imbalances. We're much more sensitive to imbalances in the wires and things like that. So we'll have to work through all of that and make sure we get it well documented.
Yeah, and for those of you who do not know, risk consequence 5 in mission language it's a loss of mission. So we don't really want to entertain a risk consequence of 5, of course. Other things that were talked about was, of course, the nose camera. Kirby led a great session on that. So I expect them to look a little bit closer on that, and that will also go into the next report. Rear view camera was, of course, discussed by Abby. There are some ideas on accommodation. Basically, the basic idea is simple. This would be viewing our solar system as an exoplanetary analog. And then there was a couple of others that came up. D-spun platform has been discussed. The daughter spacecraft was talked about a whole lot. I'm not going to touch on it here, but it's not something that we're going to have a dedicated study for. But all of those will also be documented in the report.
Pontus, can you give us 30 seconds on D-spun platform? Is it a ridiculous or is it a very elegant and simple hardware solution?
It is somewhere in between. It is still a high risk for, and Jim can fill me in here. What I'm worried about, but I'm a scientist, I'm worried about all the slip rings. It sounds like a really simple and great idea from the beginning. There are other missions that have tried this compromise. And then in the very end, they've abandoned this compromise because of the risk. I would like to see a mission like this going to this new place. We got to maintain the low risk from the beginning. Jim, you have anything else to add?
No, I think that's exactly it. It's a mechanism. And so, if you're talking about having a mechanism operating for, 10 years, 20 years, up to 50 years, there are worries, right? And especially if it's a linchpin in your science. So I'm not enthused. I'll put it that way.
A good systems engineer knows when to threaten the science.
Yes.
Well, I'm scientists not trying to push something that is artificial or wacky. Is the TR level has ever been flown?
So Casey, this is Ralph. So certainly slip rings have been flown. I mean, there was Galileo, of course, had a despun platform, and if memory serves correctly, by the time that they finally figured out all of the power transmission connections they needed and all the signal connections that were needed, there were about 110 slip rings, and there were problems with arcing. They were really worried about the aging, and it was one of these things that they made the decision, and then when they got into the details, they decided maybe this wasn't such a good idea after all, but they were way too far into the development of the spacecraft to change.
Well, also, especially if you look at long exposures, Galileo was not exactly the most stable because of that platform.
Good point.
That's a good point as well.
Excellent point.
So why don't we let Pontus go ahead and move on? And for our core team, we've been doing a lot of talking this week. Why don't we just let Pontus keep pushing this forward and see if our guests have other inputs they want to add in, since we've got each other as time goes on, but are going to have less of them.
That is absolutely. Thanks for keeping us straight. Don't be shy to speak up here, guys. Okay, I'm sort of getting in close to the end here, but one thing that has come up that I want everybody to keep thinking about here, because this is not really the STM. This is higher level than the STM. It's the success milestones along the way. I think in particular, a mission like this is very, very well suited for demonstrating these success milestones along the way. I've just scattered everything I can think of on the screen here. Oh, sorry, I have some automated timing in here. Come on, go back. To start out, as we talked about before, the formation of the heliosphere and the heliospheric boundary starts really in the inner heliosphere with the evolution of with the ionization of interstellar neutrals and the evolution of pickup ions going out. We talked about that, so we must not forget that this first milestone is achieved on this journey outward here, of course. Then images of the heliospheric boundary as we move out. Those will be groundbreaking. We've never been that far from the sun taking ENA images. And then, of course, all of the milestones as we cross the boundary. Don't really need to talk about the importance of that. That's very high. And then the very next big milestone here, at least for heliophysics and also for dust, is to take that first external image of our home. It's the ENA image of the global heliosphere, and potentially also these IR images of the dust disk. And of course, the look back as well. And then you commence with the interstellar phase. And this is really when you start dipping your toes into galactic space. And part of this is reaching and figuring out the nature of a bioshock. Is it even there? Can we detect it? The other one is reaching the hydrogen wall. Interstellar probe reaches the wall. And of course, then you get into the properties of the interstellar cloud as well, collected chemical evolution and all the other serendipitous discoveries that are waiting out there. Also along the way, I posted here is when you already start uncovering that first spectrum of the EBL and the improved understanding of the dust disk, and of course, potential KBO flybys. So I've posted a link of the Google Doc that we have here. And if anyone has any comments on this right now, I don't want to spend too much time on this. I mean, feel free to chime in here. But I really want you to encourage to think about this so we can evolve it more. Okay. And you already saw this, but once we put all of this together, I mean, this keeps coming back to us. That, you know, the science that we're doing today and during this week and over the years is really clear. Disciplines doesn't really matter. This is really where the disciplines inevitably blur together. And we've shown a version of this very simplified Venn diagram before, but now it's taking more shape, I think. Any high-level comments on this?
So Pontus, one of the things you might want to think about, and I know we've kind of struggled with this, but you know, to the extent that we're talking about the emergence of our habitable solar system, you know, at some level, and I'm not sure how you incorporate this, well, then there is a flavor of earth science that is at the core of this thing, right? Not in a direct way, but in an indirect way, perhaps.
Right.
And figuring out how to incorporate that might be worth some thought.
Yes. Absolutely right, Ralph. And I know we talked about that before. Any other comments from the audience on this? Otherwise, I'll go on. I take this silence as violent agreement.
No, give him another minute or so to just think,
digest it,
and wanna speak up, and let them be. Yes.
This is John again. Somehow indicating importance of application to human exploration.
Thank you. I think that's a good idea.
Stars, you know, we're emerging into the habitable system, you know, literally as well as figuratively.
Mm-hmm. Yep. I know I have a note taker, right?
I'm taking notes, Pontus.
That's what I thought. Thank you very much. That's what we agreed to.
You could breathe again, Pontus.
Well, it is. I hope this is still.
We've had a few people unmute themselves. Did they want to add in?
I have one question. Are you going to relate this mission to already existing missions, or missions that would exist anyway when Interstellar Probe will start its activity? What I mean here is there's plenty of air shower observatories which measure high energy cosmic ray fluxes. And those cosmic ray fluxes show actually the boundaries between the interstellar medium and solar wind. For example, the orientation of magnetic field velocity of the BB plane is very nicely seen in that. The plane perpendicular to the BB plane, well, the heliotail probably is not an issue here, but it's definitely air shower experiments can be useful at complementing the aims of Interstellar Probe.
Yes, that's absolutely right. And in fact, we have captured that at I know at least, well, only one place in the science traceability matrix, and it's exactly what you talk about, is the galactic cosmic rays. But also what has been discussed is, of course, having an imaging mission sitting inside the heliosphere. Of course, once we get out there, I don't think IMAP will have survived that long. But that is also something that needs to be emphasized. And as usual, one shouldn't sort of bake it into the requirements, because we can't, but one should emphasize the need for it. Solar wind observations goes without saying. I'm expecting there will be plenty of solar wind monitors by the time we get out there.
And do remember that ACE has been running for, Ralph, how many years?
Since what, 97, I guess?
So it's not impossible that IMAP, built along a similar architecture, parked at the same place, could still be running when Interstellar Probe gets out to 100 AU. Who knows?
Yep. Do we have any comments or takeaways from the younger audience? Feel free to speak up, because you are the leaders of all of this.
You could call on people, Pontus.
Hey, let's do this. Could we have all of our early career and student participants raise their hands? We've got Eric, Daniel,
Sonny,
Michal and Elena, Kirby, Vikas, I believe we may have lost some of them to classes as the day went along. Lissith, What do you all think? What have you seen? How do you feel about this image itself? I mean, as in terms of like appealing to a much wider audience, you are probably a bit more in tune with what people like to see today than this gray bearded man.
I guess I'll say something. I mean, not really that insightful, but I mean, I really like the graphics. They're really cool, and they like invoke like deep space and just like wonder, I guess. But I like that the mission really encapsulates many fields that we're looking to study and are very prevalent in space studies, heliophysics, planetary, and astrophysics, and astronomy. So,
thank you.
It's very promising.
Thank you.
Yeah, I can say something. I think it's really exciting. I really am really excited about what the mission can bring between what we know about dust in the solar system and in the ISM and at the edge. I think that's really unexplored, and any in situ measurements or nearby measurements could bring a lot of really important information that the space telescopes have not brought yet, and that is really relevant for our own origins. So I think it's really cool, and it has like all the heritage from Voyager, and I just think it's super exciting.
Thank you. I like how that lines up with Nikolai's comment about coordinating this with observations that would go on from other platforms at the same time. Thank you, Lisseth.
Anyone else?
I have a specific science question, actually. What are the chances of finding organic molecules at any point during this mission? I mean, I'm not expecting proteins or anything, but any like simpler organic molecules.
Ooh, very interesting. Andre, do you have any insight in this?
Not, I would say, not on the top of my head, but of course, I read again the requirements for the neutral mass spectrometer, which is to measure molecules at least to masses 300 or better 1,000, so m/z, which is of course enough to measure, I would say, simple organic stuff. We're not talking about the amino acids and that stuff, but let's say some rather simple organic molecules we definitely could measure if they are out there. Of course, it is well known if we ever get close to a comet or stuff like that, then you find a lot of organic molecules. In, let's say, in free space, I don't know, there will be some, but I would take some moment to actually study and, well, make any educated guess about the numbers and then say, how long we have to integrate to be sensitive to whatever comes along our way.
So Pontus, you actually bring up a very good question, and this was brought up initially by what was called the Interstellar Probe Science and Technology Definition Team out in 1999. And the question was raised then, and it was noted that the problem is that most of these complicated organics are not bound that tightly. And so with the speed of the spacecraft, the real challenge is how do you slow them down enough so that you don't tear them apart when you're getting them into the instrument.
I have to comment. Oh, sorry.
Yeah, go ahead. Go ahead.
Yeah, I just wanted to comment also on Vikas' question. It's not really a molecule anymore, but the dust detector can detect particles down to 10 nanometer. That's only 10 times as large as a C60 molecule. So we can really detect particles that are not able to penetrate the heliosphere and that are out there. So that is a huge thing, I think. But I don't know if you call it a molecule or dust, you know?
It will rip them apart in atoms, but that's a very good point, bro. At the velocities we encounter them, we won't actually get the molecules anymore. I've actually pinged Jamie on this directly for the IDA design, for example, but it will be able to measure very small ones, yes.
I think this touches on a very, very extremely important point, and it's the fact that once we get out there, there are discoveries that we're going to make that we don't even have questions for.
Yeah, and maybe one last point about this. Yeah, dust detector will also be very helpful, of course. The problem of fragmenting bigger molecules when you have a mass spectrometer, you have this problem everywhere anyway. So if you do any flyby at icy moons or a comet, you have this problem all the time that you need to study the whole fragmentation pattern that you get. Right. Yeah, you cannot escape this problem anyway, but then we will do our best, of course, to glue together sort of the fragments and say what are the parent molecules.
Right. I mean, you'll be able to get carbon, hydrogen, oxygen ratios and say, oh, that was a carbohydrate, or if there's nitrogen there, it was probably a amino acid.
Yeah. But I also want to make the point of infrared spectroscopy, really revealing organic molecules on the surfaces of trans-Neptunian objects and dwarf planets. Just like we see on Pluto behind me, the whole equatorial band around Pluto is
absolutely
it's organic gunk, tholin, on the surface from irradiated methane in the atmosphere.
Dude, you've got a really good Zoom link.
And
Pluto's right behind you.
And Caitlin Ahrens at the last workshop talked a bit about that. She's been leading the charge on that. So we should probably invite, and she's a young career scientist too. I'm not sure if she's on right now.
So Andre talked about the neutral mass spectrometer, but what about charged mass spectrometers? You would at least get an energy per charge measurement, even if it's a molecule from that. I guess you would need post-acceleration to measure it, but you would get a good idea of at least what the total content of that molecule is in AMU.
That's a good point. Very good point. So Ralph, I mean, the question about the impact speed and dissociating the molecules and the organics is an old one. I think, I'm not totally sure, but there have been studies that also tell us that breakup is not as violent as we think. And I'm also referring to some of the APL studies that we did for some of the proposals that Rob Gold was involved in, right?
Well, I think you're right. And I mean, I think it gets into exactly how complicated a structure you're looking at. I mean, for example, if you're trying to look at left versus right chirality, you got a problem if you break everything up. But there was, like I say, it was looked at. Part of the problem was there was no development money at the time for instrumentation to really dig into it any further. And so I don't know. I mean, there may be some other things out there, perhaps either in our field or in some other fields where that there have been some advances made where there might be some applicability there. But most of what we looked at was, gee, you need to maybe have some sort of a trap, an electromagnetic trap where you can slow these things down and then take a look at them. But that's
they did get funding a few years ago for a conical collection device that would decrease the impact energy because of the slope of the collection zone. And Rob and some folks at NASA Ames they got funding to do that for an Enceladus mission concept.
Yeah, but they probably weren't going 35 kilometers a second.
No,
no, I think they were trying to collect samples at about 10 times less speed than that.
Yeah. Can you briefly educate me? If we talk about 8 AU per year, how many kilometers per second is this?
About 36 kilometers per second.
36. All right, yeah, that's an order of magnitude larger of what you usually have if you do flybys. For instance, for Clipper and the JUICE, we're talking about 2 or 4 or 6 kilometers per second.
Exactly, yes.
Velocity. And if you convert that kinetic energy into EV per molecule, you're going to find out it's going to be on the order of 10 to 100. It's a lot. That's the bonds. So may I suggest something we try instead with do what Stardust did. Stardust learned that they had to actually do a lot of ground testing and actually simulate how particles would actually have impacted their aerogel in flight. So maybe one of the things we want to think about is actually having a ground setup that mimics our instruments in flight and be doing some of these shooting different molecules into it.
Yeah, calibrate the whole thing, yeah.
Could this be made into a student experiment? Anyway, very lovely discussion. I have 2 more slides that are a bit drier, but I think we have to move on, right, Michael?
Can I have one question?
Correct.
Please.
Do we consider some squeeze to measure the magnetic field?
Say that again.
Do we consider some squeeze to measure magnetic fields? It's linked to magnetometry.
I don't know what those are.
Squids are superconducting quantum interference magnetometers.
Yes.
Right.
Squids.
Yes.
Okay. It currently not on the table. No. I have to admit I don't know much about them.
I think people have looked at them in the past about putting them on spacecraft, and there have been, I don't remember the thread exactly, but there have always been some issues about doing that.
Mm.
I'd have to go back and look at the literature, but people have talked about it.
Yeah.
But it's been difficult because of some of the other things that you can't control in a spacecraft that you can in a laboratory environment.
Okay, let me go on. Thanks so much for all the input here. I know it's Friday and it's late for some people, so let's try to wrap this up here. I have 2 other slides and discussion points. So next steps in the meetings, right? So the next study steps on our side on a very high level is, of course, we're going to incorporate all the 100 comments that we got and the suggested changes into the STM. Then on the architecture side, and Jim, you can fill me in here, we can conclude the Helium baseline mission architecture study and then begin the augmented mission architecture study. Is there anything else you want to add to that, Jim, quickly?
Nope, you got it.
Okay, great. Then we have the next kind of meetings here. So let's spend a minute on this. I would like to encourage all the topical group leads to continue the telecons. They've been really successful and productive. Elena has already talked about having monthly tag-ups for the white paper coordination. And an idea that has recurred many times is to have an intermediate mini workshop in the late spring. Any opinions on that? Any thumbs up? Good. Because I think that's really needed for us, not only for coordinating the science, but also touching up where we're going with the architecture study. It could be 1 or 2 days. So I think we'll sit down and plan for something simple like that. And as you all know, next year we'll have the other exploration workshop, the full workshop, and the keyword there is closure. Another thing that I think we want to have is regular tag-ups with topical group leads. We've had them in preparation for this workshop. They worked really well. I think what we want to do is to reach back to the topical group leads and see if we can have them maybe on a bi-monthly basis where we'll just get together with the topical group leads and the key members of those groups to tag up on pretty much all the science aspect of this.
Are you talking about monthly or bi-monthly?
I think bi-monthly to start with, because there are a lot of other sort of small tag-ups in between.
Yeah.
Something where we get everybody together, not just group leads, but also some key members of the group, and sort of open up a little bit more.
All right.
Mm-hmm. Okay. This is a list of very high-level group actions. So the way I think we want to handle this is that the group leads, you have a great set of comments and actions, and I expect you to coordinate all of those further discussions among the topical groups, right? And in the STM, of course, we have to continue to develop that, especially measurement requirements. That fifth column or fourth column in there is currently blank in many places. I would like to have more details in there. Of course, we fill it in on our side as much as we can. The third bullet here is pretty important, I think. We heard a lot of discussions on further science here. I would like to loop back to people to ask them if the mass allocations are still sufficient on the individual instrument level. For example, we talked about plasma charge states, GCR capabilities, and geometrical factors. We have certain individual mass allocations on the instrument level for those, but we got to make sure that those are realistic. So please, in the topical group leads, please look back on that and look at it. Then two very important points. You've seen the two payloads. So number one, we sort of already discussed this, but number one, take a look at the Helium baseline payload. There are things missing in that Helium baseline payload. The ENA low is not there. Document the science trade-offs. And I heard now that getting together with ENA low, Lyman alpha, and the neutrals group is a good discussion to be had. Then also discuss and also document the science trade-off between the helio and the augmentation. That is also something that is needed. We've heard some of that, but we need that down on a piece of paper. And I think that's pretty much it. The rest we have discussed, but I want to take one last step back and ask everybody, given everything you've heard and discussed, do we have some level of consensus that we're heading in the right direction? Is there anything major that is missing? Do we need to nudge the direction? And remember, shortly after this workshop, we need to finalize at least the helio portion of the STM. Okay, any comments, go backs?
Please speak up now, because if you don't, we're going to finalize them.
Yeah. How many do we have in line here? I have troubles counting.
It's 46 right now.
46. So if we're not heading in the right direction and you want to nudge it, please let us know.
How about we do this too? The question at the moment is, are we going in the right direction or not? If you feel positive, moderate, or negative on that, type it in the chat. Type it in the chat. I mean, it's okay to tell us that we're off base. It's okay to tell us that we're a bit askew. It's okay to tell us that we're fantastic.
This is John. You might add to GCR capabilities and radiation noise. It's really very important, you know, when you get out in the interstellar medium for the superthermal measurements.
Yes, absolutely. I think that's already been noted. That's great, John. Tends to be forgotten.
I have a question. Are there any plans to use the spectrometer to check for any potential new elements or any heavy metals in our solar system?
In the current configuration, the short answer is no. These are requirements based on known elements.
Which spectrometer?
Just infrared light using spectroscopy.
I think the issue there is geometric factor, that as you go out to some of these other elements, which would likely be extremely rare, because otherwise we would pick them up anyway. You end up having to be able to integrate for very, very, very long times and actually have very, very large geometric factors, and those tend to drive your mass and your size of the instrument. I know that there's some, for example, after about 15 years of integration, there was some rare isotope. There was a rare isotope of iron that had actually been detected on the ACE spacecraft. But again, a very, very long time, and that was a very large geometric factor spectrometer. So there's some of these things that we're just simply not going to be able to do because of the overall mass and the power that are associated. But it's a good thing to note, because we need to be able to document both what we can't do and why we think we can't do them, as well as what we think that we can do.
I think the specific question was actually about IR spectrometry.
Sorry.
Yeah. And I would just throw out the ideas that in general, we're going to design, just as we've already heard, for what we think is out there, but that's no fun. one of the things, we certainly want to be discovering new things, and we can point to Rosetta at Comet 67P. They discovered O2, a molecule that nobody expected to be there. And we will certainly keep our eyes open, make the best instruments we can. And I'm not trying to just say a motherhood statement. And I hope we've got some unexpected things that rock our socks and change our paradigms. So if there's a line of trans-uranium species and for some reason pops up in our infrared spectrum, I hope that you or somebody like you finds it. But we can only do so much, that you heard. We have some limitations to our spacecraft.
And if I might use that as a jumping off point to kind of wrap things up. Heading out to New York last year for the workshop, I had the pleasure to stop by in Princeton and sit down with Freeman Dyson and talk some more about this mission with him. And one of the things that the only thing that he told me, like we talked about a bunch of different things, but the only thing that he told me was, you all have to make sure that what you do is leave this mission in a position where you can be open to discovery. That if you just put down a bunch of measurements that you're going to make, and it's all things that we know we can do and want to do, that we've kind of closed ourselves off to discovery. But if we can craft this in a way where we're open to discovery, then we'll really have done something important. And that's a real challenge. It's a real challenge with how missions are crafted and formulated and then funded. But it's a good jumping off point. All right, Pontus, you didn't have any more slides, did you?
No, absolutely not.
Okay,
Everybody's tired, including myself.
Okay,
this
cool.
is a great job for everyone. Thank you.
All righty.
Thank you, Pontus. Can I say one thing really quick? It won't be long.
Really quick, go for it.
The Google Docs that we all opened up for each of the individual discussions are going to stay open for the next few weeks. If you have any more comments, we want them. Please, these are living documents, and please add to them.
Yes, and in fact, that was going to be my first point as we wrap up. We're gonna keep them open, as Casey said, for 2 weeks. And we need more of your input, more of your comments on them. As he said, thank you, Casey, for bringing that up. The white paper meetings, I think, are going to be essential to overall success. Elena, thank you for leading the charge today and helping to coordinate that in the future. We as a study team at APL, we're on the cusp of releasing not one but 2 large reports to the sponsor on the technical progress over the last year and a half. And once NASA has had a chance to review those, I believe large portions, if not their entirety, are going to be released. And all of this we'll definitely have links to on our website. Speaking of the website, all of the presentations, including the ones that were put together for today, are available on the website, will be available on the website. The one like Pontus's will be added to the website now. And all the video recordings that we took over the course of the week as we recorded the Zoom, those will also be trimmed down a little bit to get rid of the empty space at the beginning and the end, and then made available here. If you'd like to share them with people, if you'd like to look at them yourselves to remind yourself of the discussions, we really want to make the website a sort of a central place, a clearinghouse of information for all of these discussions. We as a team internally are going to release an after action report, basically a summary of what happened this week. And we'll be kind of going through our notes over the next week or so, and hope to get that out about 2 weeks from today. And we may reach out to some of you to clarify some points as we do that. So don't be surprised if you hear from us. And finally, if you liked participating in this, if you think that we're on the right track, moderately on the right track, positively going in the absolute best direction that anybody could think of, we really want you to share this with your friends, with your family, with your colleagues, and help us to grow this initiative, this effort, this community, especially with younger folks. We are so pleased that so many students registered for this conference, that so many participated in it. And at one point, I was a very young systems engineer on a planetary mission and thought that it was just fantastic. And when Ralph McNutt first asked me to start helping out with this project and said we need to recruit young people, after a few minutes of discussion, he said, no, we need to reach down into middle schools and start getting them excited about this. This is going to take multiple generations, and I can't think of a better thing for any of us to spend our time on than something that far outlives our own careers.
Thank you very much.
Thank you, Roma. It's very good that you're here.
Oh yes, it was. I am very happy to be here. So thanks a lot for the fantastic meeting.
And I hope our paths cross soon, both yours and all of yours and mine. It's great to see you. It's great to have this positive energy flowing in, and I hope all of you and yours do well over the coming months and weeks. And with that, I think we wrap. Thank you all so much for your participation. We're very grateful.
Yes, thank you all.
Thank you.
Have a great weekend. Thank you.
You too. Thank you all.
Thank you all.
Thank you, everyone.
Andrea, bye-bye.
Bye-bye.
Goodbye.
Take care. Everybody stay safe and healthy.
Bye.
Bye.
Thank you.
Thanksgiving.
Bye.
Happy Thanksgiving indeed.
Ni hao, bye-bye.
Bye-bye.
Michael, Pontus, Ralph, Elena, we have a wrap up, just a small group wrap up.
Yep.
Meeting.
Yep. We can use the one that Alice set up. Yes.
I had a scheduled. You should all have an invitation to it.
A separate one.
Okay.
Very good.
Okay.
Very good.
See you on the other side.
You there,
Andrea? If you need me, you need to send me the invite to the wrap up.
Michael, I only invited the regular meeting planners to that meeting. Should I have Jim come as well?
Jim, if you want to join us, yes. Why don't you go ahead and shoot it, and then he can. If you want to join us for a couple minutes, it's just going to be a quick wrap up.
Honestly, I'm happy not to.
then we'll see you later. You have a good you have a good weekend.
Go ahead and send it to me. I'll join you for a few minutes. I'm just.
It's okay.
Andrea, I'm sorry. When did you send it? I think I can't find it.
All right, I'm gonna resend it to you.
Oh, please, yeah. I think I saw it, but I can't find it at this moment.
There we go. Voila.
Awesome, thank you.
Thank
See
you.
you there.
I'm gonna hop off and go there. Is there anything that you need, Michael?
Nope. Oh, one thing. I'm gonna hit. When I hit end, it'll record this here. This is a longer one, so if my computer gets wonky, I might simply get on by my phone. So if it takes me a couple minutes to get there, you'll know why.
Alrighty, thanks for the heads up.
You bet. Onward and upward.